Good evening, dear students. Today I'll be taking my second class on Laplace transform. Okay, so before proceeding into more new properties of Laplace transform, I would like to solve the homework that I had given in my last class because few of you had been facing problem in solving them. So first we'll be doing the homeworks, two problems, and then we will move on to the next properties of Laplace transform, right? But before going into the subject, I would like to tell you, you have to be very regular with the classes and you have to practice as much problems as possible, because like you know, it is not possible to do numerous number of problems through videos, right? So it's your job. You have to practice as much problems as possible so that you can complete the assignment that will be given to you in the near future. So please be prepared, right? And follow the classes regularly. Okay. Now the question those were given to you were, find the Laplace transform of e to the power at sine bt, right? This is just a one line problem. You even don't need to solve it. It is not at all tricky, because like last day we had already proved Laplace transform of sine bt is equal to b divided by s square plus b square, right? This had already been derived in the last class. And also we have seen that whenever a function is multiplied by an exponential e to the power at factor, all that happens is the Laplace transform gets shifted from the from the shifting theorem, right? What I mean to say is, we had derived in the last class that Laplace transform of e to the power at ft is equal to, where the Laplace transform of ft is equal to f of s, right? We had already derived the shifting theorem, so just applying it over here, it gets solved in one line. E to the power at sine bt is equal to b divided by, in place of s, now it gets replaced by s minus a. So it's just very simple, s minus a square plus b square. So this is your answer, right? This was your first problem. The second problem was, find the Laplace transform of e to the power minus t cos square t. Even this is not that tricky. All you need to do is change the cos square term into cos term, right? So over here we have ft is equal to e to the power minus t cos square t is equal to, right, like we know, 2 cos square theta is equal to 1 plus cos 2 theta. So we just need to apply that. E to the power minus t by 2. 2 cos square theta is equal to 1 plus cos 2t, right? So our function becomes e to the power minus t plus half cos 2t e to the power minus t, right? So now all you need to do is find the Laplace transform of this. So Laplace transform of ft becomes Laplace transform of e to the power minus t. Even this we had derived in our previous class, that the transform is a linear transform, right? So we can write it like this: e to the power minus t cos 2t. This we straight away get from the Laplace transform exponential function, like we have done in our last class. So over here we have half, and this becomes 1 divided by s plus 1, plus we have taken the half outside and taking this, Laplace transform of cos 2t is equal to s divided by s square plus 2 square, that is 4. And since we have a minus e to the power minus t factor multiplied to cos 2t, what happens is this gets translated by 1, that is, this becomes s plus 1 square. Answer. So all we have applied here is the Laplace transform of e to the power at. That straight away gives you 1 divided by s plus a. And over here we have applied two theorems. Firstly, the Laplace transform of cos 2t, and over that we have applied the shifting theorem. So you straight away get this result, right? Please do problems at your home so that you can even understand the classes better. To understand the classes better, you have to be regular with what is being taught, right? Okay, now we move on to newer properties of Laplace transform. So third, we want to know the Laplace transform of the derivative of a function. It is given by f prime t is equal to s Laplace transform of f t minus f0, right? So we need to prove this. Proof. So we start with the left hand side. Laplace transform of f prime t is equal to 0 to infinity e to the power minus st f prime t dt. This straight away comes from the definition of Laplace transform. Now integrating by parts, Laplace transform of f prime t becomes, okay, the first function is constant, integration of second function, that is it becomes ft 0 to infinite minus ddt of first integration, then you have ddt of the first function, that is minus s e to the power minus st, integration of the second function, so this becomes ft dt, right? Okay, you just, if you put the integral limits over here, you get a 0 minus a f0, right? And this becomes, a minus comes out, so it becomes a plus s, and 0 to infinite, all we are left out is this ft dt. So this in turn is again the Laplace transform of ft, so our equation becomes f prime t is equal to s Laplace transform of ft minus f0, and we have proved what we wanted to prove. Please look into the equation very carefully, because now we will be using it to derive other equations, right? So the Laplace transform of the derivative is equal to s into Laplace transform of the function whose derivative is over here minus the value of the function when the variable is 0, right? Now this will be, we will be using in further derivations. So please take a look at it, look at this equation very carefully, right? The process has been very simple. It is just nothing but integration by parts. Okay. So now I move on to the fourth property of Laplace transform. Laplace transform of derivative of order n. That was Laplace transform of derivative of order 1, but now we will be doing it for Laplace transform of derivative of order n, right? The result will be, we have to prove Laplace transform of this is what we are going to prove, right? So proof. Just now we had proved the Laplace transform of the derivative of a function. It was Laplace transform of derivative of ft. Now I'll go a bit slow. Please try to follow. Is equal to s into Laplace transform of ft minus f0. Right? This is what we have proved just now. Now, from this, directly from this equation, we can write Laplace transform of the second order derivative of the function is equal to s into Laplace transform of the first derivative minus f prime 0, right? Because if you see over here, if we have the derivative, it is the derivative of this function, right? Similarly, this is the derivative of this function. So it is just that from this we can automatically write this, right? Now what we can do, we can again substitute this entire equation over here. That is what we are going to do, is equal to s into s Laplace transform of ft minus f0 minus f prime 0. So all we have done is we have taken the Laplace transform of derivative, then we have applied it for the second derivative, because like we have seen, we have the function over here and derivative of the function over here. Similarly, we have the function over here, the function is f prime t and its derivative is f double prime t. It is understandable, right? Then what we have done is we have substituted this equation in the second equation. That is, we have substituted equation 1 on 2, right? So we have reached over here, which ends up to s square Laplace transform of f t minus s f0 minus f prime 0. Right? So now, similarly, Laplace transform of f, the third derivative of the function, is, now we'll just draw an analogy and we can solve it. Just by looking at this equation, you can understand what it is going to be for the third equation, or you can solve it in this process, right? If you do it, if you do the exact steps for this thing, what it will come up to is s cube Laplace transform of ft minus s square f0 minus s f prime 0 minus f double prime 0. So please look into the equation and you will see it has a pattern, right? What happens is the power that the order of the derivative becomes the power of the s, right? Over here it is 2, so it becomes s square, and then you have the Laplace transform of the function, and then the power of s keeps on decreasing and the derivative of the function keeps on increasing, but at t equal to 0. So over here you see it is 3, so the power of s is 3, and then we have the Laplace transform of the function. The powers keep on decreasing and the derivative of ft, the value of the derivative and the derivatives keep on increasing, and that is, first you have f0, then you have f prime 0, then you have f double prime 0. We end at a value which is less than 1. That means if you have 3 over here, you will end on 2. So if you have a n over here, we will end on fn minus 1. So from this we can finally conclude that Laplace transform of fnt is equal to s to the power, this n comes here, n Laplace transform of the function, that is the original function, Then we have Sn minus 1, like over here it was 3, 2 and 1, it kept on decreasing. So over here we had n, I have n, so now it becomes s to the power n minus 1 if 0. The second term becomes s n to the or n s n minus s to the power n minus 2 if prime 0. The third term becomes s n minus 3 if double prime 0, and it keeps on going, and the last term, as you can see, becomes like for 3 the last term is if 3 minus 1 0, right? So over here it becomes n minus 1 0. So we have completed, and see, that is the result that we wanted to prove, right? So this is the Laplace transform of derivative of order n. This is a very useful equation. We will be using it later in our later classes, where we will see by applying this a differential equation gets transformed into an algebraic equation, and then you will see the solutions of differential equations become much more simpler. Obviously the solutions of algebraic equations are much more simpler. So by using a transform on a differential equation, we can change it into an algebraic equation, and the solution becomes much more easier. So this is a very, very, very important equation. Please keep this in mind, right? Now we'll move on to the fifth property, that is Laplace transform of integral of a function. So we are just going in a sequence. First we have found out the Laplace transform of derivative of derivative of a function, and now we are going to find the Laplace transform of integral of a function, right? So what we are going to derive is Laplace transform of integral of a function is equal to Laplace transform of the function divided by s. See, the beauty over here is, in all the equations you will see, if you know the Laplace transform of the function, which is fs, you automatically know the Laplace transform of the integral of the function. The same happens in case of derivative. If you know the Laplace transform of the function, you automatically know the Laplace transform of the derivative of the function. So it is a very beautiful thing, and you can apply it very beautifully. You will see it. It's beautiful. Okay. So now let's try to prove this. Okay, so let's take the left hand side and let's start. Let ft dt is equal to phi t, right? And obviously phi 0 is equal to 0. So if you just differentiate this equation, we immediately get, therefore, phi prime t is equal to ft. Right? On differentiating the equation, we immediately get this. So we already have a relation. So we already have phi t and phi prime t, and we have derived the relation between Laplace transform of derivative of a function and the function. So we will be applying it. So just now we have derived Laplace transform of phi prime t is equal to s into Laplace transform of phi t minus phi 0, right? Just now we have derived this equation. So directly from this you can get, or so our phi prime t is ft, right? So Laplace transform of ft is equal to, and this becomes s Laplace transform of our phi t is this equation, so 0 to t ft dt right? And phi 0 is 0 minus 0. So, or Laplace transform of 0 to t ft dt is equal to fs. Fs means Laplace transform of the function divided by s. So we have proved the equation, right? So like you can see, all these equations are getting easily proved just from one equation, that is the Laplace transform of derivative of the function. So it is a very important equation, like we can see, right? Okay, so we have been doing the properties. Now I'll do each property and I'll try to solve a problem for you so that your concepts get a bit better, right? But you have to work on them. Like I have been repeatedly saying, please practice more and more problems, because everything cannot be covered in the class. You have to do you have to play a great role. So please practice as much as possible. Okay, so now the question that we are going to solve is, find the Laplace transform of 0 to t to the power n e to the power minus at dt, right? If you are asked to find the Laplace transform of this integral, so obviously we have to use the formula that we have just derived, that is the Laplace transform of the integral of the equation. But first you need to know the Laplace transform of the function itself, right? So Laplace transform of t to the power n e to the power at is equal to what? First you need to know this. In the last class, if you go on to the last class, you will see we have already derived Laplace transform of t to the power n is equal to factorial n divided by s plus, Laplace transform, it becomes s to the power, n plus 1. I'm so sorry. We have derived in the last class that Laplace transform of t to the power n is factorial n divided by s to the power n plus 1. This has already been derived. Now what happens is, our function t to the power n gets multiplied by an exponential term e to the power minus at. So we can very easily find the Laplace transform by using the shifting theorem, right? In shifting theorem, what happens? The function of s gets transformed into the function of s minus a, right? So factorial n divided by, in place of s, now we are going to write s plus a, because over here we have a minus a, so it is s plus a to the power n plus 1, applying shifting theorem. Please do mention the theorem, I'm not writing it. Okay, so now therefore Laplace transform of integral of t to the power n e to the power minus at dt is equal to n factorial n s plus a to the power n plus 1 just multiplied by a factor 1 by s, right? Because that is what we have just proved, that Laplace transform of integral of a function is equal to Laplace transform of the function divided by s. So just see how easy it becomes and how beautiful this Laplace transform tool is, that if you know the transform of the function, you beautifully and very easily can find the Laplace transform of the integral of the function. So like we have seen before, we had mentioned that these helps to solve problems in a much more easier manner. Like we have claimed before, we can see it practically that actually that happens, right? Okay. So we have solved an example. Now we will go to the sixth property of Laplace transform, that is we have found the Laplace transform of derivative of the function. Now we are moving on to derivative of Laplace transform. Derivative of Laplace transform. T to the power n we need to prove this is equal to minus 1 to the power n dn dsn fs. Okay, where it is known that Laplace transform of ft is equal to fs, right? Okay. So to prove this, we will start from the right hand side. Let's see what happens if we do the derivative of fs, right? So fs is equal to dds. Now fs is the Laplace transform of ft, so we just straight away write it 0 to infinite e to the power minus st ft dt, right? Is equal to, now we want to take this derivative inside the integral, so it becomes partial derivative, right? So it becomes 0 to infinite del s e to the power minus st. ft is not hampered by that, so it stays as it is, right? So this becomes 0 to infinite minus t e to the power minus st. The derivative becomes this, and you have ft dt, right? Is equal to so what we have is 0 to infinity e to the power minus st tft dt. So now this equation is nothing but the Laplace transform of tft, right? So Laplace transform of tft is equal to, sorry, I've missed out this minus sign over here, it comes over here, equal to minus 1 to the power 1 d ds of fs, right? So now similarly we can do it for higher order derivatives. Similarly, if we do it for the second order derivative, we will find Laplace transform of t square ft is equal to minus 1 to the power 2 d2 by ds2 fs. So if you do the same steps and if you do it for the second order derivative, you will find this ends up to this. So we can draw the conclusion that similarly Laplace transform of t to the power n ft is equal to minus 1 to the power n dn dsn fs. So we have proved what we wanted to prove, right? So we have already seen from the shifting theorem that if we know the Laplace transform of a function, we automatically know the Laplace transform of the function multiplied by e to the power at, right? Nothing changes, just that the transform, which was first function of s, that is fs, that gets transformed into fs minus a. That is what happens when a function is multiplied by e to the power at. Now we see what happens when a t to the power n is multiplied to a function, right? So if we know the Laplace transform of ft, then the Laplace transform of t to the power n ft is known. All you need to do is differentiate the Laplace transform, okay? So we will do a small problem to make the concept clear, right? Okay. So let's solve the question. Let's solve the problem. Just a second. Okay. Find the Laplace transform of, I hope you can see. Find the Laplace transform of t cos at, right? We need to find this. Okay. So how do you know what to use? Over here, what you can see, we know the Laplace transform of cos at, right? We have already found it. It is just s divided by s square plus a square. So we know the Laplace transform of cos at. Now what we say, it is multiplied by a factor t. So just now we have derived what happens when a function is multiplied by t to the power n. Over here n is equal to 1. So all we need to do is just apply the previous theorem, right? So the solution is Laplace transform of, we know cos at is equal to s divided by s square plus a square, right? This is known. Now just now what we have derived Laplace transform of t to the power n cos at is equal to minus 1 to the power n dn dsn fs, right? So just we need to apply this formula. Therefore, Laplace transform of t cos at is equal to minus 1 to the power, over here the n is 1, dn is 1, ds of fs is this. So we have s divided by s square plus a square. So just you need to do the simple derivative to get the answer. I'm not doing all the steps. We'll finally end up to s square minus a square divided by s square plus a square square. Right? So if you can understand the theorems, you can solve quite tough problems in much easier manner just by applying the theorems. So these are of great use, just that you need to be acquainted with these theorems a bit, okay? So the last we are going to do today is the integral of Laplace transform. We have done the Laplace transform of derivative, Laplace transform of integral, derivative of Laplace transform, and now we are going to do the integral of Laplace transform. This is our 7th property, that is integral of Laplace transform. So Laplace transform of f t by t is equal to s to infinite Laplace transform of f t ds, right? So we need to prove this. We will begin with the right hand side of the equation, s to infinite Laplace transform of f t ds, s to infinite, sorry. So we just put the definition of Laplace transform, and it is 0 to infinite e to the power minus st ft dt, right, ds. Now we'll exchange the integrals. We'll take the t out and put the s in, so it becomes 0 to infinite s to infinite e to the power minus st ft ds, and dt comes out, right? So it becomes 0 to infinite. If we want to do this integration, it's very simple. ft remains unaffected, right? So you have ft e to the power minus st by an minus t s to infinite and a dt, right? So this becomes 0 to infinite if t by t, you have a minus in front, so that becomes a 0 minus a e to the power minus st, so minus minus cancels out and it becomes a minus st, right? 0 and a minus okay, and dt. So all you can see is, even this is nothing but the Laplace transform of ft by t, है ना? So it becomes Laplace transform of ft by t. ft ds. We wanted to prove this, so it is already proved. Again, to understand this property, I'll do a simple problem and I'll wrap up today's class. But what we can see over here is, if you know the Laplace transform of the function, you automatically know the Laplace transform of the function divided by t, right? So we will apply this on a simple problem and try to see what happens. So the last question that we are going to solve today is, find the Laplace transform of e to the power minus 4t sine 3t by a t. So we will try to solve this. We will begin with a sine 3t. We know the Laplace transform of sine 3t. Then we will shift it using shifting theorem because we have a e to the power minus 4t multiplied to sine 3t. And after finding that, we will solve it by the previous theorem just that we have proved just now, right? So first, Laplace transform of sine 3t is equal to, it is 3 divided by a square plus 9, right? Because Laplace transform of sine at is equal to a divided by a square plus a squared. Please practice the problems, else you won't be able to understand the steps. Okay. So now we have found the Laplace transform of this. Now we can find this. So Laplace transform of, okay, fine, we'll go for this because then the integral will be much more easier. So Laplace transform of sine 3t by t is equal to s to infinite 3 s square plus 9 d s, right? So we get this from the theorem just that we have proved just now, that is Laplace transform of ft by t is equal to s to infinite Laplace transform of the function ft ds. Just look at it, that is what we have done. That is Laplace transform of sine 3t by t is equal to s integral with the limit s to infinite Laplace transform of ft, that is Laplace transform of sine 3t, that is 3 divided by square plus 9 ds, right? So just a simple step. Now you can do this integral and it comes up to, please do it, I'm not doing it right now, I'll just write the end results, and it comes up to pi by 2 minus tan inverse s by 3 is equal to cot inverse s by 3, right? So we have reached, so we've already got the Laplace transform of this portion. Now all we need to do is apply shifting theorem. So Laplace transform of e to the power minus 4t sine 3t by t is equal to cot inverse s plus 4 by 3, and it's solved. That's really easy because Laplace transform of e to the power at ft is equal to f of s minus a, where Laplace transform of f t is equal to f of s, right? So what happens? The s gets replaced by s minus a. Over here our a is minus 4, so we have s plus 4 divided by 3, right? So I end over here. So please practice problems and let me know if you have any doubts regarding this today's class. Thank you so much. Have a good night. Goodbye.